Hello everyone, thank you for coming and welcome to the new episode of the Working Software series, in which I plan to show you quite a lot of code. This session will be mostly coding. We will cover one corner case in a LINQ sequence processing, which you may encounter in practice. So this is very practical demonstration, and you will see how the problem becomes obvious, how we can detect that there is a problem in development, and then how we are addressing that problem by constructing a library which solves the problem for ourselves. This is the GitHub repo which contains that library which I am developing, but I'm not going to just demonstrate how that works. Today I planned to demonstrate how that is constructed, how I made decisions while designing that library, because that is what is really important in software development, how you make decisions. Here is the empty application where I will first remove this hello world message and then start working with some data, applying LINQ, and eventually getting stuck. I'm also holding implementation from GitHub open, and my plan is to start copying pieces of this code into the empty project so that you can see how the situation will worsen, gradually worsen for me, and how I'm going to cope with the problems. The first piece of code I'm going to copy will be, just give me a second, there's quite a lot of code here, will be the code that produces raw data. This is the main function which generates data. It is fetching as many items, and items will be string here, as the argument says. So maybe I wanted 10 strings, I will get 10 strings in the sequence. Maybe I wanted 100, I will get 100. I will work with this later. So the idea is to fetch numbers from 0 to size -1 and to convert them into human readable form. So to convert every number into the way you would write it in words, not in digits. So it's very simple. I can, since that is an instance level method, I will have to instantiate the program and call fetch, like 20 numbers or 40 numbers. And that will be the data we will start from. And now we want to do something with those data. For example, I don't know, to join them into lines and to print them on the console. For example, let's see if this basic scenario works. Here it is. So these are the numbers 0 through 39 written in plain English. So we have the data. That is nice. And we want to change those data, to manipulate those data, because we have some requirements. Still nothing bad has happened. We only have a data source at this moment, and now we are thinking about satisfying the requirements. By the way, I might move all this code into a new class, which I will call data source, just to not to look at it in the program class, nothing special. So here I will instantiate data source, and everything should remain the same. So you can imagine data source being a class which is reading a file or files DB context, a class which is reading response from a network request. So you have the data, and that is the fact you start from. And then you work on the requirements. And suppose that there is the requirement to modify these strings in some way. For example, I will define a function, a method, which will also be static in the program class. Modify string, which will do nothing right now. It will just return the unmodified line. So the point is that we need to produce a result by starting from the data and using LINQ and modifying some of those strings. Oh, this is void, this should be string, okay. And instead of printing out the data, we want to print the result. So this will be a typical situation in any software. You will modify the stream, maybe filter it where line contains letter O, and so on. Let's see what will come out from this. Oh, quite a short list of these strings. And then comes the requirement. But before that, let's define this modify, because I really want to see modified strings. If you like Monty Python's Flying Circus, then you will know that in one episode there is the King Arthur character who doesn't pronounce number 3. So line replace 3, he always says 5. Unfortunately, we will not see any distinction with letter O because there's no O, but let's try it out now. Here, so it goes 0, 1, 5, 5, 7, and so on. This is King Arthur's speech. So modify will be all right. So we have satisfied the requirements. The requirement was to produce all the numbers below 40 that contain letter E when written, spoken as King Arthur would speak. And then comes the difficult requirement. Listen to this. Also print the longest word or the length of the longest word, longest line, before and after the transformation. So we want to have max before, max after, and we want to print them out. So string lines would be this one. And apart from printing the lines, we also want to print max before and max after. How do we do that? Or maybe the maximum will not change much, or not change at all after applying King Arthur. Maybe total length or length before, the sum of lengths, and length after. Do you see the difficulty in satisfying this requirement when using LINQ? I don't have any of these right now, but here's the difficulty. Data is an enumerable. Does it exist anywhere in memory? Does that sequence exist in form of any data collection? No. But we don't know that, because that decision is encapsulated inside the data source. So it might have some array of list of strings, but it also might not have any, and construct the strings on the fly. As you pull an element from the sequence, the element is constructed anew. If you pull it, if you reset the sequence and pull all the elements again, every single element would be constructed again, even though it was constructed already once. That is deferred that is a lazy evaluation, and this fact that we are having unnumerable and that the fetch method is using enumerable range means that execution will be deferred. Nothing will happen when this line of code executes. You can imagine this enumerable data as being just a descriptor what to do to get a sequence of strings. It is not a sequence of strings. It could be a sequence of strings, a collection somewhere in memory if data source decided it that way. But we don't know. That decision is encapsulated over there. And since we don't know, there is nothing, for example, in the name of this data source class that would tell it out. Since we don't know whether there is a materialized collection or not, we must not assume that fetching data is cheap, or that it will be cheap the second time we try it out. And that becomes important when processing data. This part here, select, is also deferred, where is deferred, but this join function will effectively pull the data. This will be immediately executed operator. This is not the link operator, but it is a function which executes immediately. And it will effectively pull all the data, all the strings will be constructed and given to the function one after another, and it will produce a single string, the result of concatenating and separating with new line. We could do something totally different, like file from the system IO, write all lines and put the result over there instead of this. Both operations will effectively consume the stream, the sequence, and therefore where will be executed on whatever the select has returned after executing on whatever the data were, and that is the result of fetch. All the data will be materialized, but the collection will not be materialized. And so, if we wanted to do both operations, both to write to a file and to print them on the screen, fetching will be done twice. And let's see that. In the data source, fetch, here is the separated fetch number method, which is called for every output number. There is a call to fetch number. I did it that way because I wanted to write out what happens, how many times this is called. So if number is 0, that means that the new iteration through the sequence has started and the data are being materialized again. And if number is size -1, I will write done, so that we can see when fetching begins and when it ends. Here, fetching started, fetching done twice, because I have written data to the file and also printed them on the screen, and both operations have consumed the sequence, and therefore the sequence was consumed twice, and since it is not a collection, it was constructed twice. You could say to list over here, if you knew that you're going to walk through the sequence twice, and here it was really constructed once, remembered in form of a list. So this unnumerable over here is pointing to a list, and you can apply operators multiple times to the list without fetching the list source again. This is only going to be executed once. But what if to list is beyond the reach to us? What if we are fetching gigabytes of data. Can you store them in memory? No. So we are moving to the ground of streaming applications. What if you are solving a problem, not the problem of sequences, but a more restricted problem, the problem of streams that are very large, sometimes unpredictable in size, and still you have to consume them. I could have left that storing to file, but that's not necessary. And so we come to the problem of calculating length. It is very simple to calculate the length, by the way. It is data sum line length. We are not counting line endings. And length after is result sum line length. I did what I was asked. So we have 320 characters before, 270 after. And that's it. But the problem is that I have fetched the entire data source 3 times. When that becomes a serious problem, I'll tell you when. There will be a cost to fetching an item. Whenever an item is about to be fetched, I will sleep for that much. This will be the cost of fetching data, which is never zero. And here in the program, I will have to tell how fast or how slow my data source is. For example, 10 milliseconds per item. And by the way, here I will also keep a stopwatch. Get and set. This will be the mutable field. When fetching starts, I will start the timer, and when it ends, I will print it out so that we can see how long did it take to fetch all the data. I will time all the operations, and I will also time the commands there, and I want to print it out. This is something new. Look, now it takes time. And now it took 1.9 seconds because each of the fetch operations took 620 milliseconds. So, in order to satisfy the requirement to aggregate the sequence, to sum up the lengths of lines before and after the transform, and the requirement to print it out on the screen, I had to consume the sequence 3 times and to pay the cost 3 times. LINQ does not solve this problem out of the box. LINQ has a number of aggregating operators like sum, or those aggregate operators, general purpose ones. Let me show you. So you can aggregate, seed with 0, and say sum and line become new sum plus line length. That sum operator is effectively doing this. It's aggregating every line's length. It is attributing it to the sum, and sum starts off with 0. If I run the application, it should print the same number 270 again, so this aggregation is the same. But the problem is that aggregate operator is consuming the stream, and every aggregation operator, like sum, max, min, etc., is consuming the input sequence, and you cannot use it again unless it is constructed again. And that is the curse of aggregating operators. You can either consume your data or aggregate them, but not both. And so now we know the problem. We need an aggregation which is deferred, which doesn't execute. And when it starts executing, it operates lazily by aggregating the data that are passing by and not consuming the sequence, which means that we can, here's what I want. I want to aggregate so that joining returns both the lines that are joined and the result of this, which I want to count as int length before, so that I don't have it here. Do you understand what I'm doing here? I want an aggregate operator which returns the sequence without affecting it, so that subsequent operators can be applied. And as they are applied, the accumulation will happen. And when the sequence, the result of all the operators is consumed, for example, by the string join operator, I want to get my accumulator back. And as the lines will be the result of concatenating all the lines from the sequence, I also want the length to be the result of summing up the lengths of all the lines. I want the same rules to apply to both these results. LINQ doesn't have that. So we must invent it. So now we have a different requirement. We want to aggregate the sequence while walking through it, but without terminating it, without consuming the items. We want to tap into the stream and just listen to all the objects that pass by and aggregate them using the lambda that was passed. And by the way, seed the accumulator to the specified value. We want the same behavior as the one that is applied to the rest of the sequence. I'm not sure if I'm saying this clearly. So if join said, join me all the strings, then I want all the lengths to be summed up. But if join said, take 10, I want aggregation to be applied to the items that are being consumed. Since there is the where clause here, the where operator, take 10 will probably pull more than 10 items from the original stream. And since aggregation is coming before where, more than 10 items will be summed up. And that is the point of having length before. I also want to append an aggregate after where, and I want that one to appear as the third component in the result. Here. And now, if we took 10 items, then length before will probably be larger than length after again, because some of the items from this stage of accumulation were dropped, and length after will be shorter. And literally, this aggregate operator is supposed to put a mutable tap into the stream so that we can read what it accumulated later. But there are some difficulties there. And when speaking of difficulties, let me put it this way. Difficulties are coming from not understanding requirements right. Let's talk about the requirements. What are the requirements here? I'll go to that GitHub repo and copy the requirements from over there because I have written them there. But before that, let me tell you how you get to the requirements, how you construct the requirements. So the first thing to do is to recognize a genuine problem in capital letters, because many people forget to do that. A genuine problem is the problem that doesn't have a solution at hand. And the most obvious solution is to either use the language or the framework or to add a package that is solving that problem. So I did search Google for some 4 minutes and found no genuine solution to this problem of aggregating, of deferred aggregation, as I called it. Maybe the solution exists, I don't know. If you find it, shout out, send it over to me. The first step in solving the problem is to figure out that you do have a problem. And then you need to specify the problem in precise terms. Because very often we fall into the trap of saying, oh, there's a problem with performance, so let's try to, fix the performance problem somehow. I don't know. But that's not how you speak about problems. Yes, we do have a problem with performance, yes. But that is not going to lead you in the direction of solving it. If you think that you can brush up the performance, I don't think you will succeed. You must precisely specify the problem like I did in this situation. I want an aggregating operator which does not consume the sequence but listens to items that pass by, pulled by a different terminal operator, like this join here, and aggregates by applying the seed and the aggregation function so that it can ultimately produce the accumulated value back when iterating, when the terminating operator completes. This is very precise, a bit long, but very precise definition of the problem. And then you start designing the solution. That is also an important stage, because you will not say, oh, I know, I will solve it this way. No. You have to specify the attributes of a solution, of whatever software item we're talking about, that is a solution to this problem, without going into implementation depths. Because when you step to implementing a solution, you will have so much troubles that you will forget what you were supposed to develop. That is why we need to specify the attributes of the software item that is a solution to this problem, also known as requirements. So you will write the requirements in very precise terms, Don't forget that. Don't play Shakespeare here. This is not a place to demonstrate your literacy, but be as precise as a mathematician would be. And once you do that, offer a solution that satisfies requirements. That is it. You're not solving the problem, you're satisfying requirements. And requirements will have to include a request for an API, for a function that does that has a signature like this, because we need that. On top of that, it will have additional attributes that function implementation must satisfy, and that is the set of requirements. I will show you the requirements in just a minute. Since you're working on a tough problem, you will probably want to solve it in several steps, not just dive in, dive out, and say, oh, this is the solution to your problem. It will probably not be the best solution you can come with. So possibly you will start by implementing a minimum viable product that satisfies the requirements. It just works. It demonstrates that this can be done. Then you will notice two kinds of issues. First, it will not be nice. There is a better idea that you can apply. You will add a couple of more items to the list of requirements, like this must be way faster, this must be an order of magnitude faster, or re-implement this element or that because you have figured a better design, produce a better solution to the problem, and you will finally go to production with that solution. The requirements I came with, here they are. Deferred aggregate operator satisfies these statements. It applies to INumerable of t, any INumerable of t, the same way as any LINQ operator does. It does not cause the sequence to be iterated, so it is just a declaration, a deferred operator like select. It doesn't iterate. It returns an object to which all existing LINQ operators apply. This requirement was very difficult to come up with. Why? Could this aggregate return an INumerable of string? No, it cannot, because it needs to accumulate information. And if it did return an INumerable of string, I could for each that sequence, I could use the for each loop on that to consume it. And by doing that, the aggregated value would be lost. So there must be something else that holds both the INumerable and the aggregated value. So while talking to myself for a while and thinking how to crack this problem, I came up with the first requirement was it returns INumerable of t. After some thinking, I figured out that it's not possible to satisfy this requirement. So I came back to me as a customer and says, listen, this cannot be done. I thought of it. The language doesn't support that. You could already start thinking about, for example, languages that support mixins and say, oh, I could mix the aggregate into INumerable and return that. Yes, but there are no mixins in C#. So that solution is not applicable here. So I came with a softer requirement that there will be a result, but I request that all the rest of LINQ applies to that object. Please, I want my select operator to come next. I want where to apply to the result of that. I want another aggregate to that. I want the entire LINQ to work on whatever you return. So this is the fine dance between requirements and possible implementations. Pay attention to those details when you work on requirements, when you accept requirements. And there comes the second part, which was the reason why this request was added rather than that to return INumerable. So the request is that the resulting object carries on an aggregated value, but there is a trick here. At any moment, this value will be the result of aggregating the elements of the sequence that were iterated up to that moment. Here is the explanation. The request, which I didn't say here explicitly, but I could, which is more like an intention, make the new operator functional. Because LINQ is a functional library, and we need another functional operator. We don't want an operator which is violating the existing rules of LINQ. Of course we can make that, but somebody would be surprised using that operator to see that some usual rules that are observed in LINQ are not observed by this operator and say, oh, this library is crap, it doesn't work well. We don't want that. If we are going to extend the LINQ, then let's obey the rules of LINQ. By the way, that is the reason why there is no for each operator in LINQ. But you have to consume it and then, or just apply the right line, okay? This is how you consume the sequence with an operator which has side effects. The right line operator has side effects, it is not functional. And if you ever wanted to apply it, please step out of LINQ and do it there. There's no for each operator in LINQ, and there are no signals that there will ever be one. And that same reasoning must apply to aggregate. It must not produce side effects, and its result must be the result of seeing the elements of the sequence up to the point to which the sequence was consumed at any moment. This is very, how to say, fine requirement. If I pulled 10 elements from the sequence, I want that aggregation, I want that sum to be the sum of the 10 lines I saw. If I say move next and pull the 11th element, I want the accumulator to be affected by that one element. But here is the most important result of this requirement. If I started walking the same sequence again, I want the accumulator to start from 0 again, not to remember what happened to the previous iteration. And that is what makes it functional. And finally, repeated execution yields the same result, which means that the aggregator doesn't remember past iterations. So let me solve that problem without having this, because we don't have it in LINQ right now. So this is code as it was. One way to solve the problem, though I'm not sure that it satisfies all the requirements, but we could satisfy it, but it's going to be complicated. This solution, which I'm going to show you, will not satisfy all the requirements, especially not the last two. It will be a poor man's deferred aggregator. So before iterating, we might set length before to 0. That is the seed. And then we might aggregate length before. I might even turn this into an extension method. I'll make this class static so that we have that aggregate operator. I might put this reset here and then say for each stringle line in data, I will update length before the accumulator line length and yield return the line. So I'm not consuming, this is a deferred, this is lazy evaluated operator. I'm not modifying the sequence, I'm not consuming it, I'm waiting for somebody else to pull the data, but as the data are being consumed by a different operator, I'm summing the lengths up. We can say dot aggregate lengths before, and that's it. Here's the operator. And here, instead of printing, where is length before, instead of iterating the sequence for the sake of calculating the length before, I will just refer to that static property getter. Let me run this. Look, why didn't it? Oh, because there is Y operator, it never came to the end. This is puzzling me. Oh, no. That's because there is take operator. It really didn't get to the end of the sequence. Okay, this is it. We have two iterations. Calculating the lengths after is the second one, but the one before fetching data for a printout has disappeared, and execution time has dropped by 30%. So we have eliminated one iteration. Let's eliminate the other one. Static int length after get set. And unfortunately, I will apply that good old copy-paste pattern and risk making more than one bug, right? Hopefully this will be good. Why? Because they are storing the data in a different field. I may have added some lambda that consumes the accumulator, so to make this operator reusable, but I want to keep that implementation simple after, so that I don't have to iterate to get the lengths after. This will be joined, this will consume the sequence, and finally we will print length after. And after this, I hope to only see fetching once, yes. So if you observe, execution time is very close to fetching time. This is the deferred aggregation. It only takes a little to construct the aggregate operator, which receives those seed and lambda parameters, but that's not what I'm after. Why? This is not a solution. This is not a good solution, because if I took two enumerators from this data and started consuming them in lockstep, so to call move next on one and then move next on another, so to iterate twice in parallel, these aggregate operators would start stepping on each other's toes. They will overwrite the same location to aggregate into it. So this solution doesn't satisfy these two requirements, which are very important to me. I want true isolation between operators. I want every operator in LINQ, including my own custom operators, to work in isolation from everything else. Or otherwise, somebody will be really disappointed to find out that this operator behaves strangely when applied in parallel. And so, how do we solve the problem? I will show you very briefly what this deferred aggregation library, as I called it, looks like. You will notice that I was only satisfying these requirements one after another and doing nothing beyond these requirements, nothing. And I made the operator which can be applied to solve this genuine problem the same way as it was applied here. It was done here. The key element in solving is this aggregating enumerable, aggregating enumerable. At the very beginning, I called it aggregated, past tense, but that was a mistake, because this enumerable is aggregating as it is walking through data, continuous form. I think that this could be removed, but focus on these two methods. Map data. This is the general. So if you had an object which is holding an enumerable and the accumulator inside of it, you could map it to the next aggregating enumerable with a new type T and the same accumulator. That is the select operator on aggregating enumerables. And so you would apply a function, a mapping function, not to elements, because this is really not a select operator. You could apply a mapping to the entire sequence of T to produce the entire sequence of T new. And here is the implementation, the most engaged class of them all. Here is how it implements map data. Here. It will construct, this aggregate handle is a materialized accumulator. Just a technical detail, I couldn't solve it differently, but it will hold a produced sequence, which you will see what it means in just a second, and the same accumulator. And produced sequence is this. So there is a sequence, there is an input sequence, which this operator is wrapping, and we want to produce we want to produce the accumulator. This is the accumulating enumerable. If it was invoked twice, it will throw an exception, because by design of this library, this class can never be the object of this class can never be used twice. And that is the isolation I forced, which again you will see in just a few minutes. The idea behind this object is that it will act as in the same way as enumerator does. Whenever you want to start iterating for a sequence, you get a new enumerator object. And so it is isolated from any other iteration. You can iterate twice through the same sequence, and those enumerators should not affect each other. In this library, when you call aggregate operator, it will issue a new object of this class, and it will only consume or tap into the sequence once and never again. It will never have a chance to listen to the same sequence twice. And if it did, that is not indicative of any mistake on behalf of the caller, but it is my bug. So I had to throw the exception to defend the caller from my bugs, but this will never happen. And then comes the substance. All right, I will indicate that I was called, and this is the substance. Accumulator was initialized to the seed when this object was constructed, so I don't do it here. And I'm doing precisely that loop. This loop is what I'm doing. I'm walking through all the items, adding them to the accumulator by applying the aggregating lambda, and yield returning the item unchanged. And this is the crux of the entire solution. What used to be a static property or field and a static aggregating function has become an object, so that it is instantiated again every time you wish to iterate through data, and so every iteration will produce an isolated aggregate value. But how does that work? Innumerable extensions. This is where everything begins. I have called this operator aggregate stream. It is applying to a sequence to enumerable of t. It is receiving an accumulator, the seed for the accumulator, and a lambda, which combines the accumulator and the item into the new accumulator value. And it is returning, guess what? Not that seeded aggregate object, but seeded aggregate declaration object, which does nothing. That is the deferred operator. It just remembers these values and nothing else. But it has a materialize method, which is public, but it is coming from an internal interface. So you will, if you are using this library, you will never see that method, unless you do some reflection, but you don't have to. So materialize is constructing that seeded aggregate which is doing the job. And that is the point. Whenever you pull the data, whenever you want to map them, I will first instantiate a new issue spin-off, a new instance which holds these same parameters, and tell that instance, please do this for me, or for the caller. And that is how I'm isolating all aggregations. This operator is returning an aggregating enumerable, my own interface, not enumerable of t. So how does LINQ work? It works by defining the aggregating LINQ library, a library of methods that look and work the same as methods with the same names and arguments in LINQ. So I am tapping into LINQ and carrying the aggregated value, the accumulator, along with INumerable. If you like theory, this may look like I am creating a mixin for LINQ objects, but since they are not supported, I'm not. How does select operator work on an aggregating enumerable? By calling calling map data on a mapped sequence, which is held privately and I don't have access to it. How does where work? The same. I'm just transferring LINQ operators, regular LINQ operators, to my library, and you will never see that anything strange happened. You can write the LINQ the same way you ever did. But the aggregated accumulator value will walk along with your INumerables all the way. If you like this, you can read all this code. It's not too large, but it is terrible. Let me just show you, not this, but look at this. All generics. If you like generics, this will be heaven for you. If you don't, then don't open Innumerable Extensions class. So let me demonstrate you this. And with that, I will complete this talk. Here is the data. The same as before. I will comment this out. Let's take that same demo, and you will see how that same demo can be done. This will have to wait a bit. Okay, I think fetching data once, those same data, we have them, and now we want to aggregate them. So, dot aggregate stream, which is returning, look what it's returning. I aggregating enumerable of string and the accumulator, which is still not defined, but it will be int. So there is sum and there is a line. And now this doesn't compile. Why? Because this is not INumerable of string anymore. I will call it bar, and that will work. And if you wanted to see what this is, it consists of two. It is I aggregating enumerable of t and t accumulator, which is int. So it is containing a string and an int. And then we will select by modifying the sequence. And I want to aggregate stream again using the same. So let's create a local function. So this is accumulating length. I want to apply that. Accumulate length. So if you observe, I couldn't reuse those static aggregators before because they were using different static properties to store their data. But now these separate aggregators will add separate items to the accumulating enumerable stream, and they will not clash. Each function will add to a different variable. And you will know that because there is an override to an aggregate stream, which is only visible when applied to an already aggregated stream. So this doesn't exist here. You only have one variant here. Just give it a seed and a map. But if you're aggregating again later, you will have access to the result of previous aggregation. So it is prior and this length. I want to turn them into a nice tuple, which will be length before is prior and length after is length. Okay. And what do we have as the result now? We have an I aggregating enumerable of string and a tuple int length before, int length after. Very nice type. When it comes to consuming this stream, you can attach that. I will do these lines here. All right, this. I'll put them into a, or let me add a local function. Innumerable of string. Look, innumerable of string. Your functions which are consuming sequences will remain consuming sequences. They will never be affected by the fact that there is an accumulator going side by side with that innumerable. That is very important element of this solution. This will consume the sequence, which is the result of all non-aggregating operators, those common link operators. So you will finally say dot reduce and say how to reduce a sequence. I will delete this and this because it is done. And do you know what the result is now? A tuple of two integers. It has pulled out both accumulators as they are at the very end of the iteration of the reduce operation, which will internally consume all the lines to join them and to print them out. And accumulators will assume their final values. And those final values will be returned. And by the virtue of deconstruction, you will be able to read lengths before into lengths after and have accurate values for printout here and here. Length before, length after. So this is the result of applying the deferred aggregation library, which taps into LINQ and adds one operator to them. These familiar values 320 to 70 are here again. Execution time is about the same as fetching time. Fetch is done precisely one as requested. This is the crux of this entire presentation. I would like to hear from you. What do you think about this operator? Do you like it? Do you think it is useful? It is easy to use? Or do you know how you can solve this problem very easily? You can this print here, this one, can be turned into a for each loop, which is accumulating lengths and returning an integer. So you can modify the consuming operation to aggregate while consuming. But I do not agree with that solution because this function already has its duty. It is to print. If I added another duty, then I would violate at least one principle, solid principle. I want every function to only do one thing. So at least single responsibility principle would be violated. And also open-close principle would be violated as well. Because if I ever changed my mind about aggregation, I would have to change the print method, which is plain stupid. I will give you a real-world example from which this came to be. So I made this operator because I needed it. I needed to decode a file, process it, and encode it again. And both things are costly. They cost a lot. I mean, they cost 10 seconds per file. And you want to process files in a loop. And so if you pay 20 seconds per loop iteration, and there was an additional requirement to calculate several curves, characteristics, distributions as you progress through the file. So the requirement was to modify file's content and to aggregate a few statistics from it before and after the transformation. So this very situation is what I had. To just satisfy functional requirements, I used to decode the file, calculate statistics, and dump it, pay 10 seconds for that, then do the entire work, 10 seconds to decode a file, about 5 seconds for processing, and another 10 seconds to re-encode it back to disk, and then another 10 seconds to open the modified file and decode it and aggregate statistics on that one. So instead of paying 25 seconds, it used to cost me 45 seconds per loop iteration, per file. And then after having it functionally correct, I said, all right, this is not how you do aggregation of sequences, and there is no operator in LINQ which does that, and I didn't find a suitable library which does that either. So let me create my own. And this is the result of that. With this library, I could aggregate statistics just before applying the modification to file's content, and just after to calculate the posterior statistics, and then encode the modified file and store it to disk. So the entire added cost was just the cost of executing accumulation lambdas. And that is all. So this is all I had to show you. I hope you liked the way this library was developed. The most important element in this library is that from the outside, it boils down to next to trivial method signature, which is, by the way, the same as the signature of the aggregate operator, which we already know. It is only coming with a different promise that it will aggregate while you consume the sequence. It will not consume the sequence on its own. If you ever come to work with streaming large files, paying a lot to decompress them, to decrypt them, and doing similar costly operations, you will favor aggregating on the fly. When you get into that situation, this is the solution. Thank you for watching. I wish you all the best. I hope you enjoyed.